So the talk is based on joint work with two postdocs, Samir Kar and Bharat Thakur, and everything is there in two frequents here about peripheral Poisson boundary. You can get it in the archive. So I'll start with two examples. Whole theory I want to demonstrate or sort of explain using two basic examples. And then I'll go to fixed point and the non-commutative Poisson boundary. So there's a well-established theory about this. So then I'll start about talking about dynamics and go to peripheral Poisson boundary. So then we'll connect it with dilation theory and some main results. Go back to dynamics and see what these results mean. And then go back to the finite dimensional case. Okay. So two examples, the one finite dimensional and another infinite dimensional. And the finite dimensional here is just take the 3x3 complex matrices and the unitary completely positive map. Okay. So this is the map I'm looking at. So just move this A11 here. Okay, so that's the first block, and just move the A11 here. So it is unitary and completely positive, really. And look at the fixed point space. So let of all x, so the tau of x equal to x. So in this case, it's actually just the range of tau itself. Okay, that's the fixed point space. And what we see is the fixed point space. This collection of matrices. So here you see the A11 is same thing here. So that fixed point space is of course a subspace containing identity, but it's not an algebra in general. So here it is not an algebra. Okay, so like if I take two elements in this fixed point space, you see this way. So since this corner has to be same, right? So if you take two such things, when you multiply, okay, so AB, I can't have the, you will have, if you just multiply two matrices, like it will have this kind of form. This and this entry will not match, right? So because of that, this is not an algebra. So that need not be in F, but you can make it an algebra by modifying the product. So the last entry, you change it like this. Okay, so when you new multiplication here on the fixed point space is the usual matrix multiplication in the first 2x2 block, but this entry, you just borrow it from here, and that way it becomes an algebra. Okay. So Choi and Afros observed this phenomena in general. So in a very general context, it happens. And this new product is known as the Choi-Afros product. So you saw this, I think the first day there were two talks where this appeared. Afterwards, I have not seen it, but you may think of it as a curiosity, but so you see it means what good is it? Means okay, the fixed point space, not just an operator space, it is an algebra. How does it matter? Then you see that the algebra structure is connected with dynamics very much. Okay. So here is another example. Now infinite dimensional. So just take the unilateral shifts. Okay, on L2 of Z plus. So you take the orthonormal basis indexed by positive non-negative integers E0, E1, E2, the usual shift, the right shift, which is an isometry. So using that, so this is the matrix of V, and the matrix of V star, the backward shift. So using this V, we define a unitary completely positive map. And this is the unitary completely positive map I want to look at on B of L2. So tau of x is V star xV. So it is unitary because if you put identity here, V star V is identity because V is an isometry. And so if you act it explicitly on matrices, how does it look? So if you take any arbitrary matrix here, so with respect to that basis, starting V0, E1, etc., I start counting from 0 deliberately. I think it's important. So if you see tau of this, you see it is just shifts the whole X that way, right? So this, the first row and column disappear, and the rest of the thing, whatever is there, just gets moved up. Okay, diagonally it's shifted. That is what tau does. Now, so what are the fixed points? So the fixed points of tau, like if you want tau of X to be X itself, so then this says that X11 should be X00, X22 should be X11, X33 should be X22. That means all the diagonal entries have to be same. Above the diagonal, they also have to be same. They are all equal here. Here, everything should be equal. So this is precisely the Toeplitz operators. The diagonally, they're all same, equal. Okay. So these are bounded operators on L2, whose matrices will have this kind of form. So the diagonal entries are equal, above the diagonal, subdiagonal, everywhere. So these are Toeplitz operators. And again, they form a vector space containing identity, and that is not an algebra. Because if you product of two Toeplitz operators need not be Toeplitz. Simple example, if you take V and V star itself. So both V and V star are Toeplitz. We had written down the matrix of V. V was just a diagonal one here, everything is 0. V star was 1 here, and everything was 0. But V star is a projection onto this part. So the first entry will be 0, everything else will be 1. And so that is not Toeplitz. So it's not an algebra. But you can, as you can expect, we can make this as an algebra, Toeplitz operators. How? You just go to function theory. So you here with this operator, you can associate a function on the unit circle whose nth Fourier coefficient is an. So this is a general Toeplitz operator. So nth Fourier coefficient, you put an, you get an L infinity function on the unit circle. So that is the symbol of the Toeplitz operator. So once you have just functions on the circle, you can multiply them pointwise. So you get the L infinity algebra. It's an abelian von Neumann algebra. So f and g are two such functions, you can multiply them, and then you look at the Fourier coefficient. So that you define as your product of two Toeplitz operators. So you see, it is, though we started with really non-commutative thing, but the algebra which you get, the fixed point space here, becomes a commutative algebra. So this is what I said, you get a commutative algebra. Okay. So let's go to the general setup now. The general works. So you take any complex Hilbert space, von Neumann algebra you take inside that, and you take a normal unitary completely positive map. So I'm taking sort of the best setup. One can generalize further and things like that, but I think this is most the easiest way. So if you want to work with just finite dimensional thing, okay, you can take the full matrix algebra or any subalgebra of that, star subalgebra. So you take von Neumann algebra. So normality will be automatic there. Otherwise, you need that continuity to work with it. Okay. So look at the fixed point space. So these are also known as harmonic elements of tau, the set of fixed points. So they are eigenvectors with eigenvalue 1. Right. So since identity is always there because we have taken it to be unitary, so it is always non-trivial. So it's a non-trivial subspace. So as we can see, it in general, it's not a subalgebra. Okay. So the Choi-Frost product is a new product on this, which makes it a von Neumann algebra. So there will be no change in the norm or the other structure, the vector space structure, the adjoint, everything will remain same, the norm will remain same, only the product gets changed. And then it becomes von Neumann algebra. So natural question, how do we define this product? Well, the original product is complicated. The Choi-Frost theory, it says that there is a conditional expectation and you apply that and you get the product. And how do you get the conditional expectation? So basically you look at identity, tau square like this, tau to n minus 1 divided by n, the Cesarew's averages, and take the limit, but the limit may not exist. And so you may have to take subsequence of filters, ultra filters, and then you have a weak compactness argument and say that there is a limit and there is a conditional expectation map, and you apply that and you get the product. So I will not go into that because I want to give an alternative approach, much simpler formula for the product. So I will not go into that at all. So Izumi called this Feynman algebra, new Feynman algebra one gets, as the non-commutative Poisson boundary. He had his own justifications to call it Poisson boundary, motivated from classical things, and then he computed such things as to what Feynman algebra gets, some type 3 factors, this, that, in various examples, even on quantum groups, various examples, you look at good completely positive map and compute the Poisson boundary and sort of identify it. Abstractly, you know it is always there, but identify it and say what type factor it is and things like that. Okay. So the thing I was interested in is seeing, look at the tau, tau square, tau cube, etc. So each of them is unitary completely positive map. So it has its own set of fixed points and it has its Poisson boundary. So how does it change? Okay. So my initial thought was, okay, you have the fixed points of tau, is automatically fixed points of tau square also. So maybe you have a going correction and you get a big Feynman algebra which contains all this. But that is not quite correct. So I wanted to see how these algebras change. Okay. How are they related? But you see that if you have an eigenvector with eigenvalue -1, say tau of x0 equal to minus x0, okay, and that is possible, though we call it unitary and completely positive, still negative eigenvalues are possible with x0 not being positive. Okay, but then x0 becomes a fixed point of tau square, but not of tau cube. So they are not really increasing. Okay. So it is true that the fixed points of tau are fixed points of tau square, but then they become fixed points of tau to the power 4, not tau cube. So they are changing. So very quickly you realize that what you need to do is not only look at the fixed points, but look at eigenvectors with eigenvalues like this, tau x equal to lambda x with mod lambda equal to 1. This space, okay, eigenvector. So they are called peripheral eigenvectors. So we need to look at the peripheral ones, because like here, the -1 became here, okay, when you took tau square. So same other roots of unity also would contribute. So instead of just looking at the fixed points, we should look at all eigenvectors with modulus of the eigenvalue equal to 1, the peripheral eigenvectors. Yeah.
So you have this inclusion of the boundaries. Is the product the same? If
so that was a natural question. That is what we wanted to know. Okay, but you see that it is, to begin with, it is not inclusion. Okay. So it breaks. So we thought, okay, to an increasing algebra, you will get a big Feynman algebra, all sub-algebras inside that, so it would be nice. So, but that was not the story. So they are not increasing. So, okay, instead of that, you look at all such eigenvectors. Okay, so now if you look at eigenvectors like that, that is no longer a vector space, right? Just eigenvectors with eigenvalue equal to 1, that was a vector space, but now we have different lambdas, so they are need not be, it won't be a vector space, right? So you have to take the linear span. So you have a notation E tau equal to span of this. Okay. So peripheral eigenvectors, the span of that. So, so this is the name. So E tau is an operator system. That just means that it goes under a joint, because if tau of x equal to lambda x, then tau of x star would be lambda bar x star. So it will be goes under a joint and contains identity and may not be caused under multiplication. So well, we take the norm closure, span closure, because I work with finite as well as infinite together. So infinite dimensions, you have to take the norm closure. So the first theorem, I want to say that this p tau has a new product, which makes it a C-star algebra. Okay, the span closure of this. okay, which contains the original one, the Poisson boundary as a subalgebra. So the peripheral eigenvectors take the linear span and the closure, then that is an C-star algebra. So that we call as the peripheral Poisson boundary of tau. So the earlier one, just the fixed point, that was called as the Poisson boundary, a non-commutative Poisson boundary. Since non-commutative is there here everywhere, I'm not repeating it, just Poisson boundary. And the peripheral things, if you include, then it's the peripheral Poisson boundary of tau. Okay.
Sorry, could it be that you could define another product on E tau directly so that
Yeah.
it becomes closed?
No, it won't be closed in infinite dimensions. No, it won't be
And the
natural.
multiplication, I mean, huh?
Yeah. No, it won't be naturally closed. No. You see we are not changing the norm. Okay, only the multiplication we are changing. With respect to norm, we are not changing. Okay, so yeah.
Is also the Choi-Efros product or a different one?
In a way, it is Choi-Efros product. Okay, because Choi-Efros product here was defined for the fixed points, but since we have other eigenvectors now, so it's an extension of the Choi-Efros product. Okay, so how to compute this new product is the question. So that the dilation theory comes into picture. Okay. So what is this dilation? So the same setup I'm taking. So a Feynman algebra and a normal unitary completely positive map. Then there exists a triple K B theta, where okay. And here. So you have this unitary completely positive map from A to A. Okay, so A is containing bounded operators on H. So what we'll do, we will take a bigger algebra contained in B of some K. Okay, K is a Hilbert space containing H. So here I will get a map theta, which is also normal, unitary, completely positive, etc. But more than that, it is also multiplicative. So it's an endomorphism. So we call it, it's a star homomorphism from B to B. So unitary star homomorphism, we call star endomorphism. Okay, and how are the two related? So how are the two algebras related? So this the bigger algebra, that B, so there is the bounded operators on a bigger space. So you have H and H perp in K. So the original things are embedded like this. Okay. So elements of our original algebra, which is contained in B of H, is embedded like this. So the bigger algebra B contains things like this, but the corner of B, if you project it to the first H part, that is A. Okay. So the elements of B are always things of this kind, where this X belongs to A. Okay. That corner, the first corner of B. Okay. So that way you embed it into a bigger algebra, and that's again a Feynman algebra. So A is a corner of that, P being the orthogonal projection of K onto H. And there you have a normal unitary star endomorphism. So the CPA has been changed to endomorphism. And you have to have the dilation property. Or the two things related. So if you look at an element like this, X 0, 0. So this is in A. So this whole thing is in now B. So if you apply theta on that, in this corner should act as tau. I don't care what happens elsewhere. Okay. And that should happen not only for theta, but in power of theta.
Can you lift it a little bit? Just because Daniel is very tall.
I can shrink.
So
Yeah, you just lift it up. You don't have to write it again. You just lift the board.
Change them.
I don't know.
The bottom one up.
Bottom board.
Yeah,
Yeah.
Too high? Yes. Yeah. Okay. So if you embed the original algebra element in the bigger space, apply some power of theta, you should have the corner as tau to the power n. Okay, so it acts exactly like tau on that corner. Okay. So, and this derivation is unique up to unitary equivalence under a natural minimality condition. I'm not going into, not writing it, but a very natural thing. You get a minimal extension, which we call the minimal derivation, and it's unique up to unitary equivalence. Okay. So I should say a little bit about what is this derivation theory. So it's actually motivated from classical things, from Markov processes. So in classical Markov process, what happens? Like the Markov chains, you start with a stochastic map, right? Your stochastic matrix, the matrices, non-negative matrices, entry-wise non-negative, and the row sums are equal to 1. So those are stochastic matrices, which when you apply on CN, you see it is a unitary completely positive map, right? So, and you start with one such or a whole semi-group of them, and then you construct the Markov process, right? That itself is not a Markov process. It's a semi-group. People say that that has a Markov, but that is not the Markov process. So once you have the stochastic map, okay, or a semi-group, you construct the Markov process. The Markov process is constructed using the paths or the trajectories, and you put a measure on that using Kolmorov's consistency theorem. You get a measure on that, and then you have the filtration, how the thing progresses, an increasing family of sigma fields, and then you have coordinate random variables there, and a conditional expectation recovering the CP map or the original stochastic map. Okay. That is how the classical Markov process works. Similarly, starting with the UCP map or a semi-group, sorry for the typo, one can think of a quantum Markov process, like the measure space will have to be replaced by a Hilbert space and the filtration of projections or filtration of subalgebras. And then one can have a family of homomorphisms or conditional expectation maps like that. Similar, one can build whole theory of quantum Markov processes, just analogous to the classical one. Okay. So there is a long history of such quantum Markov process. So like Accardi and many others. Like the Hudson and Path-Sartre theory was Martin was talking about, which is a sort of very concrete representation of some of these processes, okay, in Fock space. So there is the minimal one here, which is called as the weak Markov flow, okay, and that comes basically from the CP map by a repeated application of Stein-Spreng's theorem. See, the Stein-Spreng's theorem gives you this kind of lifting from a CP map to a homomorphism, but it's sort of one-time one. It doesn't apply to the compositions. Okay, so this lifting is sort of the derivation is one which works for all powers of tau, or if you have a semi-group, for the whole semi-group. Okay, so it's basically Stein-Spreng's theorem. So a repeated application of Stein-Spreng's theorem. Okay, just like the Kolmorov's theorem there, here you need this repeated Stein-Spreng's theorem. So that way we get. So here you see, I had in the classical case you have probability space, then the filtrations, and then random variable. Similar thing you get a sort of triple. Okay, we get a Hilbert space and a family of projections, and that conditional expectation map was the one you are seeing there. You see, looking at just the corner. That is the conditional expectation map here. From the whole thing, you just look at PXP.
So even if your original algebra is finite dimensional, this other one will be infinite dimensional.
Yeah, naturally infinite dimensional. Because even classically, you see, if you are even have a two-step transition, okay, just tossing a coin. But if you are doing it repeatedly, then you need the infinite.
In the Madeline's talk, we saw an example.
Yeah. So true. There are, and okay. Now the thing is that many people would like, okay, I got endomorphism, why not automorphism? Okay, because quantum theory want to have reversible dynamics, so want to have automorphisms, and somehow in the classical setup, it's not natural, right? So like you say, you start a Brownian motion at the origin, okay? You don't say what happened before, right? You just say you start at 0, okay? You don't insist that it must have started earlier and you should have followed Brownian motion before also. You don't say that, right? So, so this way, the first part acts naturally. So, and then if you sort of translate from the process from time t to t plus s, that way if you translate, that gives you the endomorphisms actually. So you see the process from 0 to infinity, then some t to infinity. And there is that shift, the time shift, that is what is giving you the endomorphism. So I would note that there is an endomorphisms and connect with the theory of Poisson and Powers, because they are studying semigroups of endomorphisms of B of H. So those semigroups of endomorphisms of B of H, called E0 semigroups, can be constructed out of CP semigroups now. And it was a big advantage because you see CP semigroups you can write down even on 2x2 matrices, right? Non-trivial CP semigroups. Whereas if you want to write non-trivial semigroups of endomorphisms, you have to go to Fock spaces, this, that. It's semigroups of automorphisms you can write very easily. But if you want proper endomorphism semigroups on B of H, then you need Fock spaces or some other constructions. Okay. So this helped us to get more examples of E0 semigroups. So further derivation to automorphisms, people insist, and then it is possible. See, the Markov process, this construction here means non-unique, means there are people doing it in different ways. Like to what is conditional expectation, people have different definitions and different ways of embedding the original algebra in the bigger algebra. Sometimes like this one was a non-unital embedding. Okay, the original identity is not going to the identity. Some people would like that to be unital embedding and things like that. So there are many differences. So most of the time, if you insist on automorphism, it can be extended to the negative time and get automorphism. So typically it is possible. So sometimes it depends upon the conditions you need. Sometimes it's not possible. But even when it is possible, then it becomes non-unique. Okay, there are a lot of choices. Okay, so but this part is the sort of the weak or the minimal part is contained almost all the time in all the directions, and that is what gives you the statistics actually, the expectations, the repeated expectations, everything is actually determined by the minimal part. Okay, so the other part is sort of extra just by our insistence that we want automorphism. So there you get non-uniqueness. Okay, so let me continue. So that is general theory. Now we want to apply that derivation theory here. So let us go back to the yes. So we have a unitary completely positive map now from A to A, and we dilate it like this. So X gets embedded here. And you have a semigroup endomorphisms, and you can come back by this P. Okay. So if you do that, here at this level, we are looking at the span closure of this all X, so that tau of X equal to lambda X with mod lambda equal to 1. We are looking at this space here, which I called as E tau. Now we have the similar thing E theta here, right? So just as E tau here, we have E theta here. The eigenvectors with eigenvalues of modulus 1. Okay, span closure of that. Now this is an algebra automatically because theta is multiplicative. Okay, and you can go between them. So, so the theorem is that if you start with an eigenvector here, X, okay, tau of X equal to lambda X, it can be lifted to an eigenvector X hat here of the dilation, and in a unique way. And conversely, if you have an eigenvector here, you can compress it and get an eigenvector here. Okay. So that is what the theorem says. How much time I have? 15 minutes.
Yeah, 5 minutes.
So if you have an eigenvector here, with okay with the modulus 1, then you can lift it to an eigenvector. So and it compresses back. Moreover, this lifting has this property that the norms are same. Okay, then x hat actually looks like this, x and something else, but still the norm would be same. Okay, and moreover, even if you take linear combinations of these eigenvectors, the norm would remain same. Okay, so that requires some proof. But once you have that proof, then you can say you define the product here by just lifting. Okay, and compressing it back. Okay, so the new product x circle y, you just lift them, multiply, and compress it back. Okay. And that way, this algebra, the new algebra you got, is nothing but this C-star algebra, okay, which is automatically a C-star algebra. The peripheral eigenvectors of theta, the span closure, is automatically a C-star algebra. You just compress it, and you get this. Okay, so that is the new product. One curious thing here happens is that I took norm closure. I didn't not phenomenon algebra, right? So the phenomenon algebras would like to have phenomenon algebra because you started with this and a normal UCP map and would like to have phenomenon algebra. Strangely, it is not possible. Okay, so look at this topology algebra example. So if you want to have peripheral eigenvectors, so I want to have x star x equal to lambda x. So that, I don't know, s and v is same. Okay, so it means that these are like just earlier we had the topology operators, similar things, but similar things. But now you look at this kind of thing. A0, lambda A0, lambda square A0, this kind of things. Okay, A1, lambda A1. These are called lambda topology operators. So we called it as lambda topology operators, and then found that in literature someone has already called them as lambda topology operator. So I'm surprised, but anyway, we kept it the same. So the dilation is nothing but you use the bilateral shift. Okay, so you can lift it to the whole thing, and so natural dilation is the minimal dilation. And the phenomenon algebra generated by this, so this kind of things, you have two-sided things now, will be whole B of K. So you cannot compress that to B of H and keep the norm same. But on this part, the span closure of this lambda topology operators, the norms match. Okay, even for topology operators, it's a non-trivial result. Topology operator, you lift it to the two-sided thing, the norm remains same. But now it is true also for the linear combinations and their closure, but not to the weak. So, and you may also, whether we can lift other eigenvectors. So in general, that is not possible. Since when you want to lift here, you have to multiply by lambda inverse, lambda minus 2 like this. So that is not possible if mod lambda is less than 1. So only the peripheral ones can be lifted.
This
In
is
general.
related to not having a normal shift invariant state, right? If you had a normal invariant state for your S by S, you would have a phenomenon.
Yeah.
But here the shift doesn't have a normal state on that Hilbert space.
Yeah. Okay. So this formula, so this is a natural formula for the extended Choi force product. But if you look at the dilation theorem carefully, I get a new formula. So if you look at two eigenvectors, say tau x equal to lambda x, tau y equal to mu y, the x circle y can be computed directly like this. Apply tau to the power n on xy, multiply by lambda mu to minus n, take the strong limit. So with this formula, you can actually forget about the dilation. You can say, okay, my formula for the product on eigenvectors is this. Okay, simply by this formula. Okay. The funny thing is that I don't know how to show the convergence of this limit without going to the dilation theory. So but this limit should always exist. So in very general setup, any phenomenon algebra, any UCP map, this limit would exist for all peripheral eigenvectors. Okay. So I would be very happy to see some proof without derivation theory. So one of the consequences is that if the of this formula, if you see this, this formula, so you can really forget about the derivation and just look at the formula. Then you see that if the original algebra is abelian, the new, so this I call as a peripheral Poisson boundary by taking this closure and with the new product. So that is automatically abelian if the original one is. Also, if you have two peripheral eigenvectors, then the product is also satisfies this. Tau of x circle y is lambda mu times x circle y. So that in particular means if it's the lambda mu is not in an eigenvalue, then the circle y must be 0. So if I restrict the UCP map inside this peripheral Poisson boundary, that is an automorphism. Okay, so from that follows that it's an automorphism. So you have this new C-star algebra. On that you have this automorphism tau. Okay. So if you see the dynamics now, go back and see the problem you wanted to see, how tau, tau square, tau cube, how it changed the. So now I'm looking at the whole peripheral Poisson boundary, and that is not changing at all. Okay. Peripheral Poisson boundary of tau, tau square, tau cube, they are all same, they are equal. That is the static. It is only the some eigenvectors for moving from eigenvalues, some like roots of unity coming back here and becoming fixed points and things like that. But if you look at the whole space, it is just static. Okay. So you don't get a bigger phenomenon algebra or anything. It is just the same one. What we start with tau, the same thing remains. Other things are subalgebra. So skip the proof. So we can also ask, now I go back to D cross D matrices, where I would like to have the case, when does the new product same as the old product, right? Because we said, okay, we have to define a new product, but there are cases when the new product is same as the old product. So one important case where it happens is that if tau has a faithful invariant state, then it is automatic that the new product is same as the old product. So initially we thought, okay, this must be the necessary and sufficient condition. And actually we looked at literature and some mistakes also, some places which said that this is equivalent to that, but it's not true. Okay, it's not true. But this is true that if it is a faithful invariant state, if it's there, then it is the new multiplication and the old multiplication are same. But in general, this is a theorem in D cross D matrices. If you look at the chi cross decomposition, okay, the peripheral automorphic, that means the two products are same if and only if this happens. So every eigenvector, peripheral eigenvector, is given by this kind of commutation relation with the Krauss operators. So YLI should be lambda LIY. So you can see if you have this kind of commutation relation, then that becomes an eigenvector. Okay. So conversely, if only if all the eigenvectors are of this kind, then it is peripheral automorphic. And this is a special case, then it happens, but not in general.
Is this with respect to the new product now?
No,
Automorphic on the.
yeah, it is automorphic with respect to the new product. Yes, this is just a definition saying that the new product and the old product are same. So in this case,
Sorry, yeah, I forgot.
yeah. Okay, so so now we are in finite dimensions. What happens if you look at the MD D cross D matrices? So you have the peripheral eigenspace and the rest. So you can decompose MD into two parts as a vector space orthogonal direct sum. We don't have an inner product there now, just a vector space direct sum. And so is the peripheral space, and the other space is the sort of the nilpotent part, all those x where the limit is 0. So MD, every vector will break up as a direct sum. It's a sum in a unique way, one part in the peripheral part, another part where it goes to 0. And the good thing is that this does not change with the powers of tau. If the same decomposition works for tau, tau square, tau cube, etc. There is no change.